Hello the internet and welcome to my channel. On the bench today I have a power supply. This is a brand new power supply. It's a Seasonic SSP350 ST power supply, and this is a replacement for a faulty power supply that I found in a sound device, and you're gonna see the video or the full refurbishing process on this channel at some point. Now, as part of the refurbishing process, I'm also swapping the fan of the power supply with something more reliable and more powerful, because one issue with this sound device is just it doesn't have ventilation inside. It relies on the ventilation of the power supply, and you don't need to be an expert to know that you can't rely on the power supply cooling solution to cool down a whole case. Now, unfortunately, I have electrical noise coming from the fan, which I can see on the output, on the sound output of the sound device. So in this video, we're gonna tinker with fans and filters and wiring, different approaches in connecting the fan to the power supply to try and minimize and hopefully remove this electrical noise that is being picked up by the output board. Now, the reason for me to replace the fan inside the power supply is number one, that the original fan is not the best quality. I can't even find the datasheet of this fan. Number two, it doesn't have a great airflow, even at full speed. And you have to consider that this, as it comes from the factory, is thermally controlled by some circuit on the power supply. So this would spin very, very low, very, very slow out of the box. So that doesn't work for me. But even if I wire it directly to 12 volts, it doesn't really move a lot of air. So to catch two birds with one stone, I just went ahead and purchased a good quality Delta fan. This is pretty high power, maybe too much, more of that in a second. And the idea was to bypass the thermal control on the board, or maybe just wire the fan directly to 12 volts. So that way the fan is acting as cooling for the power supply, but also cooling for the whole system. Now, the original idea was to wire the fan to the existing fan connector here. It's a little 2-pin, I think it's a PH connector, one of those things that we find in computers and everything. Now, the fan connector here is driven by this little transistor here you might be able to see, which is getting 12 volts on one end, and it gets some sort of temperature signal, I'm guessing, and that's it. And then it's driving the fan depending on temperature. But when I went to wire this much beefier fan onto this connector, well, I realized that the 12 volts line wasn't actually coming straight from 12 volts. It was going through a little resistor there, which you might be able to see. It's a 2.2 ohm resistor. It's a 1206 SMD resistor. And I thought, wait a second, the original fan, which is this one, it's basically drawing 96 milliamps when running at 12 volts at full speed, while this one, with the replacement I purchased, is drawing 550 milliamps. So I thought, wait a second, what's going to happen to that little resistor? Am I going to overheat it? So I decided to go ahead and just wire the fan directly to 12 volts, but in doing that, the electrical noise that the fan is inevitably introducing by the fact that it's spinning around is going to the 12 volts line and to the rest of the sound device, which happens to be a vintage computer from year 2000 basically. And unfortunately, the manufacturer of this device didn't do a lot to filter those electrical interferences, so I end up with a little bit of noise coming from the fan into the sound outputs of the device, which I really would like not to have. So today we're going to experiment with different fans, because again, this is too much, I don't need this one, and most importantly, with some filters to try and either minimize or potentially reduce the noise that the fan is introducing into the 12 lines that eventually is being picked up by the output board and goes into the sound outputs. So I have a replacement fan here. It's a slightly different model. As you can see, it's missing the S. It's a AFB 1212 H instead of SH. I guess S stands for whatever, but this is more or less, it's less than half the power. This is only 233 milliamps compared to 550 something, and this is probably plenty for what I need. This one, to be honest, by running at full speed, it was running too fast. Also, it's just my gut feeling, but these massive fans running at like half an amp is generating more noise, more electromagnetic noise or interference or whatever you want to call it, because it's beefier. It has a bigger motor in it. It requires more energy to just spin around, so that means bigger electromagnetic field, I guess. I'm not an expert, so feel free to comment down below if I'm saying rubbish. So I'm hoping with a combination of a slightly less beefier fan and adding some filters through on the 12 volts line here, we are going to get a good result. Now, number one, I would like to see this noise so we can do something and hopefully we can ascertain whether we've actually achieved something or not. So first thing first, I got my oscilloscope here, which is on a tablet this time because I like to do this on a single camera. It's on FFT mode. The idea is, let's see what happens with this fan, which is the beefy and super fast fan, when it's wired directly to 12 volts. So it's not going through any filter or anything. This is just going to run at 12 volts full speed. I'm going through my current limiter and isolation transformer, by the way. If you don't know what you're doing with power supplies, please don't work with power supplies. There are lethal voltages inside those things. So this is not a tutorial. If you decide to do this, it's you take responsibility and blah, blah, blah. Now, let's power up the fan and see what the oscilloscope is reading with the fan just wired to 12 volts. 3, 2, 1, go. Hopefully the noise is not going to be too loud from the fan, but you can still clearly see all sort of spikes here, all sort of harmonics, starting from, we have all the frequencies here, 100 Hertz, 200 Hertz, and up to what's number 10. Number 10 is 1.3 Hertz. And this is definitely the fan, because if I disconnect the fan here from this little connector I have, now the fan is disconnected. As you can see, the noise is mostly gone. You have a little bit of spikes in here, but I think I found out that this is just a power supply not being loaded. Because if I plug a hard drive in it, this goes away. I'm plugging a random SATA hard drive, just the SATA connector, and have a look at those little spikes here at the, say, at the low frequency section. Hard drive is spinning. You see that? I mean, yeah, maybe, maybe not. But yeah, we still have that one, which is kind of concerning. I have number 2, which is 101 Hertz. So that's, by the way, one of the frequencies I was seeing on my spectrum analyzer. So before we move on to the other fan or whatever, I have here, let me disconnect the hard drive. I know it's not going to like it too much, but anyways, I have here a motherboard. And I'd like to properly load this power supply and see if by any chance that noise is going away. So let me turn it off first thing first. Let me remove mains, because you never know. And then I'm going to wire the power supply to the motherboard. So at least I have all the lines, 5 volts, 3.3, 12 volts, minus 12. Everything is going to be loaded somehow. All right, I got the motherboard plugged in. The fan is still wired in because I want to see whether it's working. Then I'll unplug it. 3, 2, 1, go. 70 watts. Do I see any? No, I still see this. Like, what are those frequencies? But 50, 99, and 200 Hertz. Let me unplug the fan, because obviously we have a fan on the motherboard as well, and we don't want that. Has it changed anything? I would say no. The power supply is still running. I've got 70 watts coming out of my socket, so we still have a little bit, but not much. Okay, so we'll kind of ignore those frequencies for the time being. It could also be because the power supply is completely open, there's no case around it, there's no ground, by the way, because I'm going through my current limiter, isolation transformer actually. So for the time being, let's ignore those things, but let me go back to the fan real quick. And it's pretty obvious that this fan is introducing a lot of noise. Now bear in mind that each one of these little division is 10 dBs. So if this is my base level, we are talking something about 30 dBs of noise at some frequencies. So first thing first, let's test the new fan I have, which is a bit slower, a bit less beefy. So hopefully it's going to be a bit less noisy than this one, number 1. And yes, I'd say it's considerably less noisy. We are talking about, I would say, less than 20 dBs of noise. So this is a good starting point, because that means we have to deal with much less noise than we would have with this fan. And honestly, I feel, obviously I can't show you on camera, but the airflow of this fan it's enough, it's quieter, and it's not half an amp running. So this is completely fine. So how do we solve the situation? Well, we need a filter, and in this case we're going to use an RC filter, resistance capacitor filter. As the name suggests, we're talking about a resistor and a capacitor that basically act as a low-pass filter. So it's only passing frequencies below a specific one, which can be set with depending on the capacitor and the resistor, and will definitely let DC pass, because DC is like 0 Hertz. It's the lowest frequency that you can get. Now this is a little contraption that I made for some other projects. It's my little RC filter for fan noise, by the way, and it's made of 2 resistors and a diode for polarity protection and the capacitor. And this is, I can't remember what's the frequency range. I'll show that you in a minute. I might use this on something else. But on this power supply, with the help of DJ Marek78, if you know the channel, you know he's my little consultant behind the scene. Thank you very much, Marian, for all your continued help. Please take a look at his channel. It's in Romanian, but Marian started making English videos, so please do take a look. We've come up with the idea that this 2.2 resistor, 2.2 ohm resistor, which I didn't know what it was for, it's part of an RC filter, because obviously we have filter capacitors on the 12 volts output. These 2 capacitors here are 2200 microfarad capacitors, so in parallel they make for 4400 millifarad, which is quite a lot. And with the 2.2 ohm resistor, which offers a very, very low voltage drop, this is an RC filter. Now, how do I calculate what kind of frequencies we are talking about? Well, obviously there are online calculators. This is the RC calculator from DigiKey, so something you can find online. Now, if I put like 2.2 ohms of resistance and 4400 microfarad of capacitance, I end up with -3 dB cutoff frequencies of 16 Hertz. That means that a filter made with these components, it won't let anything above 16 Hertz to go anywhere. It will basically filter them out. Everything below 16 Hertz, which includes DC, includes the 12 volts DC basically, will be left untouched. Everything above 16 Hertz will be filtered off. Now, obviously, this is a filter, so it's not like 15 Hertz is totally fine and 20 Hertz is being cut completely. No, this is the -3 dB. There should be a graph somewhere. Yeah, there we go. That's more or less how it works. There is a slope going down, so that means that if the -3 dB cutoff frequency is 16 Hertz, obviously you're still gonna have some 20, 40, 50. So hopefully by the time we get to 100 plus Hertz, the filter is gonna be effective, and all those harmonics that we saw here on the FFT analyzer will be gone. So first thing first, let's wire the new fan, the less powerful fan, to the fan connector. So that's going to use the RC filter. But before I do that, I'll have to remove that capacitor because I want the fan to get 12 volts or more or less 12 volts all the time. So let's do that. Alright, so the transistor is removed. Let me show you how it works. This pin here on the left is wired to ground, and I'm touching the ground from the power supply. There we go. And the other one is wired to, I think, this one. No, maybe the other one. No, maybe this one. Yeah, there we go. I have continuity with this one. Now, one of these other pins, I think is this one, is wired to the this side of this 2.2 ohm resistor. There we go, we got continuity, and the other side of the 2.2 ohm resistor is wired directly to 12 volts. You won't be able to see it, but I'm touching 12 volts now. There we go. So 12 volts come in, it goes through this 2.2 ohm resistor, it's going to this pin here, and then we got the output through the tab of the transistor into the connector. So all I need to know to basically fully connect the fan, not directly to 12 volts because we have the 2.2 ohm resistor, but more or less directly, is to jump the tab with this pad here. So let me do that real quick. And I happen to have a 0 ohm resistor, 0805, so that might actually work well, like elegantly. Let's put it away. Yeah, why not? What do you think? I mean, otherwise I can use a wire, but it's not going to be very elegant. And now if I check the resistance between the 12 volts output on the connector and 12 volts itself, it should read 2.2 ohms. There we go. It's reading 3 point something because these probes are reading 1 ohm by themselves. So obviously you need to add it up to the thing. So it's 2.2 ohms indeed. All right, the fan is wired and I'm ready to try. Now, my only question mark, my only concern is what kind of current or power is that 2.2 ohm resistor rated for? I don't know, there's no way to know. Usually that's a 1206, usually 1206 are kind of beefy resistors. It also obviously depends on the traces on the PCB. Obviously the component by itself can't really dissipate much. You need proper chunky traces on the PCB to dissipate. So we're gonna check with the thermal camera in a minute, but I have some replacements, half a watt replacement for that 2.2 amps. So just to be on the safe side. But right now, I wanna make sure that the noise has been reduced or possibly gone completely. And let's turn on the fan. 3, 2, 1, go. Okay, fan is spinning. Oh no, I still have the noise. No, no, I still have the noise. It didn't go away. That sucks. That really sucks. Now, just out of curiosity, what's the voltage drop on that 2.2 resistor? I think my calculation said something about just less than 1 volt. Half a volt. Okay, so the 2.2 ohm resistor is dropping half a volt of voltage. So I'm not sure exactly what's going on here. My next little test is to basically add one of my filters. I fitted a 5.6 ohm resistor and 1000 microfarad capacitor here. This should make an RC filter with the cutoff frequencies of 28, but that's not what matters. What matters is that two RC filters in series, they basically increase the slope of the cut. So the other one, I can't remember, was like 18, 16 hertz. This is 28. So that means that at 50 hertz, they both cut, which means the slope of the low pass filter is steeper. So hopefully that's gonna cut more by the time the fan is introducing noise into the circuit. I'm not particularly optimistic because I think that one filter should have been enough. But let's try this. Hopefully I got everything in the right polarity. Let's turn on the power supply and the fan. 3, 2, 1, go. And I think it works. I think it does work. The first two spikes here, those are there with or without the fan. I mean, the simplest way is to stop the fan. And you can see that that really doesn't change. But there's nothing else coming out here. Amazing. It does work. It needs a steeper filter. I wasn't expecting that, to be honest. But at least it works. To be honest, I was hoping to not have to use this, because now I have to find a space for this inside the power supply or maybe just outside. I was hoping to be able to just use the RC filter on the PCB, but unfortunately there's not much I can do for that. I mean, what I could do, because that is we said 2.2 ohms and 4,400 microfarads. So it has a cutoff frequency of 16. I can't really, I mean, increasing the capacitance is going to be a disaster. I could increase the resistance. I mean, I don't mind the fans being a bit slower. That would lower the cutoff frequency, which means at the higher frequency that we could see the noise before, well, the filter would be more effective. But there was so much noise, I don't think that moving the cutoff frequency by 10 hertz is going to change much. And with both the 2.2 ohm resistor on the board, on the PCB, and my little resistor here, which is a 5.6, we end up with the fan receiving 10.5 volts, which, to be honest, I don't mind. I think it increases the life of the fan, and I think the airflow provided by this big fan running at 10.5 volts is more than enough. It makes it a bit quieter, and again, it will last a bit longer. So I guess that's my solution, and I'll have to make it look as nice as possible. Now, one advantage of having another resistor on the line is that now the voltage drop on my 2.2 ohm resistor should have reduced. So we had half a volt earlier on, I think it was, and now we have 0.438. Let's see how much power that would be. So that would be 87 milliwatts, and honestly I think that any kind of 1206 resistor that Seasonic put on that PCB is going to be totally fine. I don't need to replace it with an half a watt resistor. But just to be on the safe side, I'll get my thermal camera out and we'll make sure that there's nothing happening in that area. Thermal camera is out, and what you see there is basically the 2.2 ohm resistor, which is definitely the hottest part of that PCB. You can probably see that. If I'm going to rainbow, then it's red on red. You can clearly see that area there, it's warmer, but it's only 34 degrees, so I'm not really concerned about that. Yeah, as you can see, it's only 35 degrees, so that is absolutely fine. And the 5.6 ohm resistor on my additional filter is also totally fine. This is a 1 watt resistor, it's only 40 degrees. Again, the thermal camera obviously it's highlighting any glimpse of warmth, but this is not a concern at all. Perfect, it works. Now, since I'm here, I'd like to test this fan as well. This is an 80 by 80 15mm fan, and I have another one of these power supplies. It's still a Seasonic. It sells under a different name, well, a different model, not a different name, still a Seasonic. It's a slightly different model. But it features an 80 by 80 fan, and I thought it would be a completely different power supply, mostly because I think it's like £20 more expensive, but it turns out it's exactly the same PCB, just with slightly different heat sinks, simply because the 120mm fan sits here, so it needs more space, while the 80 by 80mm fan sits here, so they can put bigger heat sinks. And I ended up buying the one with the 80 by 80mm fan just to see whether by any chance it would do different noises. It was easier from a noise perspective, electrical noise, not physical noise. But it turns out they are exactly the same power supplies. So I'm going to swap the fan on that power supply as well for the reasons that I mentioned at the beginning of the video. And this is the one that I selected. It's 15mm, but it's pretty powerful, but not crazy powerful. This is measuring, it's written here somewhere, 174 milliamps on my bench power supply when running at full speed, so yeah, it's not too bad. And I would like to see what kind of noise this makes directly connected to 12 volts, you can see here, and then we'll wire it through the filter here, and we'll see whether the noise is going away completely as with the 120mm fan. Now, the 120mm fan was 233 milliamps, this is 174, so obviously power consumption is not a problem. We won't have a problem with those resistors. We didn't have them with this, we won't have it with this. So fan directly connected to 12 volts, 3, 2, 1, go. And yes, we do have some noise, you can see that here, it's not a lot, but we definitely have something. Now, let's wire this to the RC filter, the additional RC filter, and see what happens. Yeah, I think it's effective as the other one. We still have those little spikes here, but again, those are coming from the power supply apparently. Now, one last thing I'd like to check on this power supply, which is more or less unrelated to the noise problem, is the minus 12 volt line. This very power supply, it was reading borderline to the ATX specifications, because ATX allows plus or minus 10% on minus 12 line, which is, I would say, secondary line. It's not so important. But on this power supply, when the system was working, it was going down to minus 10.9. And again, the minimum is 10.8. That caused a little bit of drama with my little sound processor, but you know, in theory, this is within ATX specifications. Now, I see there, you won't be able to see, I'll show you if I can. Hopefully capacitors are discharged. There is a 7912. So that's negative 12 voltage regulator, linear voltage regulator. So I'm not expecting anything which is far away from minus 12 volts. The linear voltage regulators are very inefficient. They warm up a lot, depending on the voltage coming in, of course, but they do deliver spot on voltage most of the time. So first thing first, I want to check what kind of voltage am I getting with no load, as it is right now. Let's measure here at the ATX connector what kind of voltage we're getting. And we're getting minus 11.7, which is, to me, that's totally fine. I still would expect something closer to minus 12, to be honest, but it's nothing, it's nowhere near minus 10.8 that I was reading on a live system, on a working system. So let me check the pin out of the 7912. There we go. So the 7912 is facing that way. Let's put it that way. So that means that this is my output. No, it's not. No, of course. So that means that this is my output. And we got indeed minus 11.7. Now, what are we getting as an input? That is why. So the input is more or less minus 12. We got minus 12.3. Then we have the voltage drop introduced by the semiconductor inside, which is, I guess, it's more or less half a volt. I mean, we can check that. Yeah, we got 0.6 volts as voltage drop, which is unavoidable, of course. So to have a more accurate output, we would need to have, so that's the output, right? No, that's the input. That's the output. Yeah. We would need to have a higher input. Sorry. I'm not entirely sure what happens when the system is up and running. Maybe the input also goes a bit below 12.3, minus 12.3. And that's it, you know, the linear voltage regulator cannot increase the voltage, you can only decrease it. Okay, well, I guess it's not the end of the world. That's it for today, I guess. That's what I wanted to do. I'm really happy, well, happy-ish. I was hoping to be able to reuse the filter on the PCB without having to add another one. So I guess I'll go ahead off camera. I will prepare the spark supplies with the extra filtering, the new removing the transistor on both, because I have another one which is in a case right now, and that's it. We'll see what happens. We'll see how they work. I'll put on screen right now. Once I'm done, all the outcome of the power supply, the outcome with the fans, the outcome with the noise at the output of the sound device. And to be honest, if it works, it works. If it doesn't, there's really not much I can do about this. I think I've invested enough time on this power supply and trying to remove noise from this fan. So that's it. I hope you enjoyed this video, this simpler edited video with just everything on a single cam, the oscilloscope, the thermal camera, internet, everything. It saves me quite a lot of time in editing, and the goal is to make more videos. I probably wouldn't have done this video if I had to deal with multicam and picture-in-picture and lots of different feeds, one for the oscilloscope, one for the thermal camera, one for the browser. It takes a huge amount of time to edit everything together. So I hope you enjoyed this, don't want to call it new style, but alternative style. Let me know what you think about it down below in the description. Let me know what you think about the video, about this, what we've done so far, whether you've enjoyed it. And don't forget, I'm on Patreon, Facebook, all the links are down below in the description, all the usual junk, you know what to do. And that's it for today. I hope you enjoy your day, and hope to see you soon here on my channels for my next videos. Thank you very much. Goodbye. Bye-bye.